Good morning. Today, my presentation is titled Diagram2Structure, a DiagramDiff framework for offline diagram understanding. Diagrams are widely used in scientific research, education, and software development, such as flowcharts, mind maps, and state machine diagrams. They can visually represent complex structures and logical relationships. However, many diagrams exist only as images, which we call offline diagrams. These diagrams lack structured data representations, making them difficult to reuse, edit, and understand accurately by large language models. Existing diagram editing tools can generally be divided into three categories. The first category includes direct manipulation tools such as PowerPoint and Visio. Although they are intuitive, users need to repeatedly adjust the position, color, and connections of elements, which makes the operation tedious. The second category is programming language-based tools. These tools support rapid prototyping and automatic layout optimization, but they have a high learning cost. The third category is large model-based tools such as GPT-4o, which can generate diagrams from text. However, when dealing with existing offline diagrams, they still have difficulty accurately recognizing structures and reliably executing complex editing commands. For offline diagrams, there are also some existing recognition and stroke recovery methods, but they still have clear limitations. Template matching-based methods rely on predefined template sets and cannot handle unseen diagrams effectively. Semantic segmentation-based methods can distinguish regions of different colors, but they often suffer from broken strokes and have difficulty processing intersecting strokes. Online diagram recognition methods can achieve relatively high accuracy, but they require stroke order information and cannot be directly applied to image-based offline diagrams. To address these problems, we propose the DiagramDiff framework. Its goal is to transform offline diagrams from ordinary images into standardized structured data, thereby improving the ability of large language models to understand and interact with diagrams. The overall method consists of two main modules. The first module is the offline diagram stroke reconstruction model. It first performs image enhancement, binarization, and thinning on the input image. Then, it divides the strokes in the diagram into multiple segments and classifies, groups, and reconnects these segments based on information such as endpoints, angles, and curvature. Furthermore, we design a split-point detection method to separate incorrectly connected strokes between different diagram elements, reconstructing more natural, continuous, and structurally correct online strokes. The second module is the diagram recognition model. Since strokes recovered from offline images may contain jagged edges and positional offsets, their attributes, such as centroid and curvature, may be inaccurate. Therefore, we introduce a diffusion model for feature enhancement. Specifically, the model uses image features as the core information and stroke attributes as conditional information. Through deep feature fusion in the diffusion model, combined with a graph transformer network, it achieves instance-level recognition of diagram elements. Finally, we can obtain standardized structured data, including nodes, edges, text, directions, and connection relationships. To evaluate the effectiveness of our method, we construct the Diagram2A dataset, which contains 100 offline diagrams and 500 question answering and editing tasks. It covers different diagram types, including flowcharts, mind maps, and state machine diagrams. Experimental results show that DiagramDiff outperforms existing methods in both diagram stroke reconstruction and diagram recognition tasks. In addition, user studies demonstrate that when the structured data generated by DiagramDiff is provided to large language models such as GPT-4o, Claude, and DeepSeek, their accuracy in diagram question answering and editing tasks improves significantly. For example, GPT-4o's accuracy increases from 71% to 90% in editing tasks and from 77% to 92% in question answering tasks. In summary, our work makes three main contributions. First, we propose a high-accuracy stroke reconstruction method for offline diagrams. Second, we introduce an instance-level diagram recognition method based on diffusion model feature fusion. Third, we construct an offline diagram question answering and editing dataset to evaluate the diagram understanding ability of large language models. With DiagramDiff, offline diagrams are no longer just images. Instead, they can be converted into structured data that large language models can understand and manipulate, supporting more complex semantic reasoning, logical verification, and diagram editing. That concludes my presentation. Thank you.